For the organizers for giving me this opportunity to speak about my recent work. This work based on this is a talk based on work I did with collaborators in the last few years. Let's see. Just to give the background, little background, otherwise straightforward stuff that Einstein favored action for lambda CDM cosmology given by this action here. From this action, varying respect to the metric, one can get this kind of Einstein equations. We're going to use this usual convention that the speed of light in 8 pi g where g is the Newtonian gravitational constant will be normalized to unity. So we know that these equations are a system of 10 coupled linear hyperbolic electric partial differential equations, and because of the fact that these equations are at most second order derivatives in the metric, GR is usually referred to as a second order theory of gravitation. I'll just give you some description of the 1+3 covariant approach, where the dynamical and kinematic quantities are decomposed into spatial and temporal components, and we have two types of derivatives involved in the field equations that we're going to see in a second. We have the time derivatives of tensorial quantities defined in this manner, project respect to the four-velocity vector. We have the projection tensor HAB that will define our spatial derivatives of tensors in this manner. We'll use the notation that this kind of round brackets will refer to symmetrization over the indices A and B, whereas these square brackets will refer to anti-symmetrization. And this angular bracket will now refer to this orthogonally projected symmetric shear-free component of tensors or vectors. Okay, maybe we define volume element of three rest spaces orthogonal to the four-velocity vector by this quantity here, which we will now you will see we use to define curl of tensors, vectors of tensors, the covariant spatial divergence and curl of those tensorial quantities will be defined as such. And we will split the covariant derivative of the four-velocity vector into this acceleration, expansion, shear, and velocity terms. Defined in this manner here. The Riemann tensor is defined the usual way, where we have these Christopher symbols, the Ricci tensor, and the Ricci sphere defined usually again. And we have the trace-free part of the Riemann tensor defining the so-called wide conformal curvature tensor, given by this expression here, which will be split into symmetric trace-free electric and magnetic components, EAB and HAB, which will play in the covariant analysis that we're going to look at defined in this manner as well. The first term, the electric component of the Weyl tensor, is usually associated with the tidal, the free gravitational field, which is responsible for tidal forces, whereas the magnetic component is the one that we know is responsible for the propagation of gravitational waves. And because of this unique feature, this does not have a Newtonian. The one does not express gravitational radiation in Newtonian physics. These are some differential identities that are used. So if you feel like you need to follow the calculations properly, the notes are already, the talk is already in Dropbox, so you can just refer back to this differential identities when necessary. So we know that the line element between two space-time points is given by this kind of metric, and on large scales, we assume the universe in standard cosmology in the concordance model is almost homogeneous and isotropic, and therefore described by the three-dimensional local metric. We have the energy momentum tensor sourcing the energy momentum, or the energy content of the universe, and we have this continuity equation telling us how matter evolves in expansion. To close this equation, we need a relationship between the isotropic pressure and the energy density of the universe, provided through the equation of state, where W here is the equation of state parameter. And so GR describes the kind of concordance cosmology that I briefly described, but despite success in explaining certain special astrophysical phenomena, we all know that it has three very crucial shortcomings, namely the nature of expansion, both during the early universe and the late universe. We have no mechanism of explaining dark matter production, and we also need to have a consistent theory that combines gravity with the other three fundamental forces of nature. So this, we think that GR is somehow incomplete, and among those attempts to come up with a better theory are the so-called fourth order theories, higher order theories of gravity in general, more specifically the fourth order theories, such as f of r theories given by this kind of action. Because of the form of the action, we have suitable choice for defining the action to explain the kind of cosmological expansion history one wants to explain, but more freedom also comes with a cost. One has to check the viability of those models, both observationally and theoretically, and the kind of analysis that I want to do is the theoretical aspect, namely the consistency of the field equations provided by those gravitational models. So in the same way that I said from the action one can come up with the Einstein field equations for general relativity, one can do the same for f of r theories, and it's usually written in this more compact form where the matter and curvature energy momentum tensors are defined in this way respectively. And there are some boundary conditions that have been mentioned over the course of the conference about the nature of those models of f of r, which I do not need to bore you mentioning again. The kinematic quantities provided by the curvature momentum, energy momentum tensor can be defined in this way, given to second order. And the total thermodynamical quantity can be given as the sum of the one provided by matter, including radiation, when I say matter, and the curvature fluid components. If we split the Bianchi and Ricci identities using the 1+3 composition, we can get the so-called evolution equations, which uniquely determine the covariant variables on some spatial hypersurface at a given particular time, T0, for example. And we have the constraint equations that must be satisfied for the quantities, the thermodynamical quantities to remain satisfied at all times. We have this also Gauss-Bonazzi equation that we will be looking at some point that I thought is worth mentioning here. So in terms of the covariant consistency analysis, we're going to look at different models of theoretical models, obviously, that are interesting to look at. One of those is the fact that the shear quantity that I showed from the decomposition of the covariant derivative, the 4-velocity vector, plays an important role in the dynamics of fluid flows. One of those earliest remarks made by Kurt Gödel was that shear-free time-like heuristics on spatially homogeneous universes cannot expand and rotate at the same time. And this result was later generalized by George Ellis to include inhomogeneous cases of shear-free time-like heuristics. And an interesting aspect of this is that those conditions I mentioned here do not actually hold in Newtonian gravity. Although we know that Newtonian gravity is just a special limiting case of general relativity. So one would expect that if that condition holds in GR, should also hold in Newtonian gravity when the special condition does. Now, since we are looking at shear-free cases, we set this guy to 0 here, and if we look back to the evolution equation for the shear, that will now turn into a constraint equation rather than an evolution equation. And the point is, how do we know that if we have a new constraint equation here, the whole set of evolution equations propagate consistently? So to check for consistency, both spatially and temporally, we take the curl of that constraint equation here and propagate that quantity that we find by taking the curl. And the result gives us this kind of relationship between the expansion and the vorticity terms. And what this equation clearly tells us is that if this product of 3 terms, theta, omega, and this term in the curly brackets is to be 0, we either have to have at least one of them 0, or all of them, or both this and this. So it followed that we must have either this term here 0, or the term in curly brackets 0 for the field equations in modified gravity to propagate under the shear-free assumption we get. Now, if we look at this term here, so one of the earliest results one can comment on this by just looking at this is that the Ellis condition we just mentioned does not necessarily hold, provided that this term here is non-zero. Provided that this term here is 0, rather. Because if this and these 2 terms are multiplied by 0, we can get a 0. So that doesn't necessarily mean that we don't have a universe that does not expand and rotate at the same time. Now, if we assume a spatially flat curvature, okay, if this term is 0, and this term is also 0, meaning vacuum universe, then we can see that the Ellis condition can already be avoided without any contradiction, meaning that we can have a universe that's spatially flat and vacuum, and expanding and rotating at the same time. So that's for the flat case. If we have a universe, flat means a universe with this kind of energy density, one can also get a model of f of r that can explain a universe that expands and rotates at the same time, provided that the form of f of r is given by this expression here. If we compare this expression to the term in curly brackets, this term here, one can actually reduce the form of f of r to a stiff fluid in r cubed gravity. So for a stiff fluid in R-cube gravity, there exists a flat in the universe that can expand and rotate at the level of linearized fluctuations. So this tells us from the consistency analysis we just made, we can already see that there are more features that f of r shares with Newtonian gravity than general relativity does with Newtonian gravity. So that's an interesting result to make note of. Another investigation we made is to find out those classes of non-rotating fluid models in f of r gravity. So if we set the vorticity to 0 in the field equations we saw earlier, turns out that there are no inconsistency issues that arise. So all the rotational fluid models in f of r gravity are consistent. So to look for inconsistencies, one has to be more specific what kind of irrotational models to look at. This is also the case in general relativity. If you turn the vorticity off, you don't get any inconsistencies, unlike the shear condition. So if we specialize to dust spacetimes characterized by this equation, including the anisotropic equation set to 0, and if we assume shear-free, we get this kind of constant equations, which in general relativity would have meant that the electric part of the Weil tensor will also vanish. But in f of r gravity, since this term is generally non-zero, one does not get a vanishing electric part of the Weil tensor. Now, if we go back to one of those constraint equations, I don't need to go back there, you can refer to it. You get, if you take the curl of that quantity, you will get this kind of relation. These two relations are actually identically the same. So this term is an identity by virtue of this expression here. And if we also go back to the constraint equations and take those assumptions we made here, we see that the heat flux for f of r gravity is irrotational because of those identities there. If we combine that with the fact that the heat flux can actually be given is proportional to the expansion, the gradient of the expansion, we see that the source, the potential that sources the heat flux can be written in terms of the expansion parameter like that. Now, if we use that, the result we just saw, to one of the constraint equations, one can actually get this kind of relation, which in the GR limit would mean a homogeneous expansion, but in f of r gravity is not generally the case. Another investigation we made is to see what kind of rotational dust spacetimes are described by f of r gravity, provided that the divergence of the magnetic component of the Weil tensor is 0. That's the necessary condition for the propagation of gravitational waves, by the way, for the existence of gravitational waves. So if we prescribe that condition here, the divergence is set to 0, we get this kind of relation between the potential that sorts the heat flux and the expansion and the shear parameter in the case of non-vanishing shear. And a subclass of such models called purely radiative models is a divergence-free, comes with a divergence-free electric component of the Weil tensor. If we have that condition, we get this kind of constraint equation, which in general relativity would mean a homogeneous, spatially homogeneous f of r model. But putting those constraints in f of r does not necessarily give you spatially homogeneous model. Another interesting part one can look at is what kind of non-expanding spacetimes exist in f of r gravity. Just for theoretical purpose, one actually gets, doing similar consistency analysis, that only models of f of r with this, that satisfy this equation can be viable for non-expanding models. We have so-called quasi-Newtonian and anti-Newtonian universes that are described by this kind of expression for the quasi-Newtonian model, where the magnetic components of the biotensor doesn't exist, which come with two set of integrability conditions that do not necessarily have to be identical in general in fourth order gravity, but it turns out that for f of our models, the two integrability conditions are identical. And for the case where only the electric part of the biotensor is zero, but not the magnetic component, these models are not, they are known not to exist in general relativity, but these models, known as anti-Newtonian models, are allowed in f of r gravity, provided that this constraint equation is satisfied. Should I continue? Okay. Another model one can study is the so-called shear-free anisotropic models in f of r gravity, where the energy momentum tensor is characterized by this guy here. Here we have both acceleration in the vortice term 0. In that case, if we take this kind of equation of state and where tau and lambda are known as relaxation and viscosity terms, okay? And we assume that those two terms are, well, the relaxation term is negligible, which are usually valid near thermodynamical equilibrium, one can get this kind of constraint equation between the models of f of r. So this equation tells us that even if the matter anisotropic tensor vanishes, no constant curvature geometries are guaranteed, unlike in general. I think I'll just stop.
So we have time for questions now.
You mentioned that when the shear vanishes, the Weyl tensor, the electric part of the Weyl tensor should vanish as well in GR. That's it.
When the shear vanishes? No, not necessarily. Depends on which GR model we're talking about.
No,
if it's just
it was a confusion of mine. I thought you said so. That, okay. So
yeah, we have to carefully look. The point is we have to carefully look at the field equations and whether they properly propagate when we make assumptions of a shear-free or a rotation-free or all those kind of assumptions. Yeah.
More question?
So there are cosmologies that you obtain in this framework that you can all obtain in simple GR, and which are they?
Yeah, there are lots of models according to this analysis. There are lots of models that do not necessarily exist in GR, but that
are they observable? Can you based on observation, can you see them, or are they just?
Yeah, that's also the point. I mean, if there come observations, let's say in the future, that describe models of universes that are not explained by general relativity. Such, for example, if one could, in principle, observe anti-Newtonian universes, if our universe were shown to be anti-Newtonian, means GR does not.
Okay, so what do you need? Do you need to show that the universe is anti-Newtonian? That's what I'm asking. So, how do you observe it? From CB, from you know?
I don't know.
There isn't anything.
It's up to other people to come up with ways of testing whether the universe is anti-Newtonian.
There isn't anything which shows the relativity of GR at the moment. So it's, I mean, operationally, it's no evidence yet. So I don't see how you can see the difference. Right?
Well, kinematically, all these universes are different, right? So even if you observe null geodesics or light rays, and you have this peculiar geometric structure, you should be able to see, for example, in lensing. I mean, if you have an anisotropic universe in which there is no shear, then the first thing that happens is that your lensing is going to be distorted, right?
Yeah.
Right. I was curious to know if you think.
Yeah, I really know about the observational studies. how people can test things. I was just curious about the kind of theoretical viability options one can have to study those different models. Okay.
Are there more questions? If not, Alvaro, announcement?
Yeah, just now that you are all